Okay, so we're going to have a look at an interesting paradox in statistics, or at least it seems like a paradox until you understand what's going on. So if you imagine I'm interested in determining whether a certain coin is biased in favour of tails, I've flipped it 6 times, I've got 5 tails in a row and then a heads. So using this data, we're going to have a look at this from 2 slightly different perspectives, and then you'll find the results will be quite surprising. So the first method we'll do is going to be just sort of the natural binomial hypothesis test. So if you say let x be binomial, 6 trials, and p probability of getting tails, so let this denote the number of tails you get from 6 flips. So your null hypothesis is going to be that this probability p is 0.5, that it's fair. And your alternate hypothesis, because we're interested in the coin being biased in favour of tails, this will be that p is greater than 0.5. So let's have a look at this then. What we do is we assume the null hypothesis is true, and then we look at what is the probability of getting our data or something more extreme. So the probability that x is greater than or equal to 5, the probability of getting 5 tails or 6 tails. So this is the probability of getting 5 tails plus probability of getting 6 tails. And then you can write this out with your formula or use a calculator here. 6 choose 5, and then a half to the power of 5 times a half to the power of 6 minus 5, which is 1, plus, and then 6 choose 6, and then 0.5 to the power of 6 times 0.5 to the power of 6 minus 6, that's just a 1 there. So to the power of 0 gives you 1. And then when you calculate this, it will give you 0.109375, because this is quite a lot greater than 0.05. So what we're saying is here there's roughly a sort of 10.9% chance of getting our data or something more extreme if the null hypothesis is true. So this isn't that unlikely, it's certainly much more likely than 5% chance of happening. So therefore we do not reject the null hypothesis in favour of the alternate hypothesis at the 5% level. So now let's look at the same data, but imagine we collect the data according to a certain rule. So let's say instead of just flipping 6 times and getting this data, we actually decided that we would keep flipping until we got the first heads, and then we would stop at that point. We'll say that we got the exact same data as before, so we got 5 tails in a row, and then we got 1 heads. So now it makes much more sense to actually use a geometric distribution for our hypothesis test, because we're not really counting up the number of heads, number of tails you've got from a fixed number of trials. You're counting the number of trials that you've done until you've got a success. So here, for method 2, if we now let y be geometric with parameter p, denote, so we'll say it's the number of flips, so including the final one where we get heads there, until we first get heads. So as before, our null hypothesis is just going to be that p equals 0.5, that the coin is fair, and our alternate hypothesis is going to be that p is greater than 0.5, because we're interested in being biased in favour of tails. Okay, so let's do the calculations now. So the probability of getting our data or something more extreme, we write this slightly differently now, because we're saying the probability of it taking 6 flips or more extreme than that, so taking even longer to get your first heads would be more extreme in favour of it being biased in favour of tails. But then, if you're clever, you notice that getting 6 or more flips until you get your first tail, this is the same as getting tails on the first 5 throws in a row. And then this is just 0.5 half to the power of 5, and then you work this out. This is 1 over 32, or 0.03125. So now this is quite interesting. We've got actually a much smaller probability than before, 0.03125. And this is actually less than 0.05. So therefore, what we're saying is the data is actually very unlikely to have happened at this 5% level. So it's less than a 5% chance of this happening. So therefore, we reject the null hypothesis in favour of H1, the alternate hypothesis, at 5% significance level. So how have we managed to get two different conclusions from the same data? Well, because we carried out two different hypothesis tests, one binomial, one geometric, and we've got the first one telling us that the coin perhaps it isn't biased, and the second one telling us that it is biased in favour of tails. So it's interesting because with the geometric one, the key sort of difference between this and the binomial test is that with the geometric you haven't decided how many trials you're going to do. With the binomial you have decided you're going to do 6 and then you're going to stop. But for the geometric one you don't decide exactly when you stop, you're just going to start as soon as you get the first heads there. So this sort of subtle difference here is actually enough to make a really big difference in terms of the conclusions you can draw from the exact same data. So for the binomial setup, if you get tails, 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 heads, we treat this as being exactly the same as all the different orders, where you get 1 heads and 5 tails, and so on. And we're working with x greater than or equal to 5, so getting greater than or equal to 5 tails. This is basically our data or something more extreme. So we group together all of these. There are 6 combinations here. But then we also group this together with tails, 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 getting 6 tails in a row. So this is what gives us a chance of 7 out of 64. So there are 7 possibilities here, and then it's a probability of a half to the power of 6 for getting x greater than or equal to 5. Then if we look at how you would group these together for the geometric one-sided test, so there's the same chance of each of these things happening. So independent of how you're collecting the data, what you're doing with it, how you're interpreting it when you stop, the chances of getting 5 tails in a row and then a heads is just a half to the power of 5 times another half. So it's always just 1 out of 64. But then in the geometric setup, you would treat this one as here y would be equal to 6. Here y would be equal to 5 for this second one. This one we get heads on the 4th trial, so y would be equal to 4. And then this one getting 6 tails in a row, you don't know what y is, but you know that y is greater than or equal to 7. And then the ones that I've not drawn here, y equals 3, 2, and 1. So actually, in order to have y greater than or equal to 6, so this was our kind of our data or something more extreme, you're only looking at this option and this option. So this is why the probability of this happening is only equal to 2 out of 64. So this is where we got around 3%, and previously the 7/64th, this was around 10.9%. So we get a much lower probability for the geometric one because of how we've grouped the data, which is very interesting. And actually, while there's some very interesting maths at play here, it's actually quite a serious kind of issue, because if someone wants to mislead you with statistics, perhaps they won't be entirely honest about how they collected their data when they decided to stop collecting data. So they might want to say, yeah, this coin is biased in favour of tails. If they use this rule, maybe this is going to skew the data in favour of it being biased, even if you collect the same data with a different data collection rule. So if I show you this data, 5 tails in a row and then heads, hopefully you can now appreciate the importance of asking how I gather the data, how I decided when to stop collecting more data. Because if you don't have that information, as we've seen for this example, the data can lead to very different conclusions.